Hello my dear students, myself Rajendra Garashe. I have done M.Tech from Indian Institute of Science, Bangalore. I was the All India 7th ranker in the GATE examination and I am working as a faculty at ACE Engineering Academy, Hyderabad. So in this session, we are going to discuss the important concepts and some questions related to the subject Power Electronics, and for the exam TSPSC Polytechnic Lecturers, right? Yeah. So let us start with the syllabus of TSPSC Polytechnic Lecturers post. So here they have given the syllabus. First is semiconductor power diodes, transistors, thyristors, TRIAC, GTO, MOSFET, IGBT. Alright, all these are the power semiconductor devices, or you can say the switching devices. Alright, but if you check in the BTech level also, you might have studied these devices. As long as the previous year question papers are considered, you will get the most of the questions related to the switch SCR, related to the switch SCR, or you can say the thyristor, right? Thyristor is a family of devices consisting of 4 layers and 3 junctions, and in that family the most popular member is the SCR, silicon controlled rectifier. Okay, so apart from the SCR, you are having the study of power diode. Power diode is a basic building block, right? Diodes are the 2 layer and 1 junction devices. After that, we are having the transistor family devices like power BJT, power MOSFET and IGBT. Okay, transistor family devices are having 3 layers and 2 junctions. Next to that, we are having the thyristor family devices, SCR, TRIAC, GTO, all these are the thyristor family devices. Okay, right. Next, static characteristics and principle of operation. Triggering circuit, triggering means turning on. Commutation circuit, commutation means turning off, right? Turning off. So till this point, these contents are related to the power semiconductor devices. Next to that, we are having the phase controlled rectifiers. Rectifier is the circuitry which converts input AC to the output DC. It is like a AC to DC converter. Okay, again in that we are having the different types of the rectifiers: single phase, 3 phase, single phase half wave, single phase full wave, 3 phase half wave, 3 phase full wave, etc. Right? Very important chapter, phase control rectifiers. Very vast chapter, and you can check, you can find the more number of questions on this chapter particularly. Okay. Next, bridge converters, yes, fully controlled and half controlled dual converters, right? So till this point, we are having the chapter number 2, that is the AC to DC converters. Next, principles of choppers. Chopper is the circuitry which converts fixed DC to variable DC. Okay, so in this chapter we are having basic chopper circuitries: step down chopper, step up chopper, step up step down chopper, and those basic chopper circuitries are having some drawbacks. So in order to overcome those drawbacks, we are modifying those circuitries, and after modification those are renamed as buck converter, boost converter and buck boost converter. Okay, right. Next, inverters. Inverter is the circuitry where input is a DC, output is a AC, right? In the inverter we are having half bridge inverter, full bridge inverter, 3 phase inverters, pulse width modulation techniques, right? Single PWM, multiple PWM and sinusoidal PWM. Apart from that, the current source inverter is also there. Next, cycloconverter. Cycloconverter is also known as a one stage frequency changer. Alright, here input is AC, output is also AC, but generally cycloconverters are used for the frequency changing, right? Next, AC voltage controllers. AC voltage controllers. Input is a AC, output is a variable AC. Here in case of cycloconverter also, input is AC, output also AC. Here also input AC, output AC. Then what is the difference between these two? Here it gives output in terms of variable voltage, keeping the frequency constant. It gives output in terms of variable voltage as well as variable frequency, right? But in practical case, these are used only for changing the frequency, all right? Yeah. Now this is the syllabus they have given, and these syllabus are generally summarized in the different chapters. Yes, first chapter is power semiconductor devices. In this chapter, yes, generally we study the different switching devices like power diode, power MOSFET, IGBT, GTO, TRIAC, etc. All right. Next, AC to DC converters, that is a rectifiers. DC to AC converters, that is the inverter. DC to DC converters means chopper, and AC voltage regulator, and last one is the cycloconverter. Okay, but if you check previous year question papers, most of the questions you will get on these 4 chapters only. First 4 chapters are very important. Almost 95% of the polytechnic questions you will get on these 4 chapters only. Very less weightage is there for these 2 chapters. Very less weightage. Okay, not only for your polytechnic lecturers, but for your TSPSC, Janco, Transco, even for GATE and ESE also, right? These 2 chapters are having comparatively less weightage, right? Next, so now we are going to revise the concepts from the chapter power semiconductor devices. Okay, right? So classification of power semiconductor devices. So power semiconductor devices are classified based on driver circuit used in the device. So based on the driver circuit used in the device, there are 2 types of the devices: voltage controlled devices and current controlled devices. Yes, voltage controlled and current controlled. Yes. So in a practical case, which devices we are having? Those are controlled by using the voltage. Yes, power MOSFET. Sometimes they ask the question, which of the following are voltage control devices? Power MOSFET, IGBT, right? These are the voltage control devices. Current control devices, yes, SCR, GTO, TRIAC, BJT. These are the current controlled devices. All right. Power diode or diode is an uncontrolled device, right? Yeah. So voltage controlled and current controlled. We know na, BJT is a current control device, and which current controls the BJT's operation? The base current controls the BJT's operation. All right. Next is classification based on carrier used in the device. So based on the carrier used in device, there are 2 types: majority charge carrier and minority charge carrier devices. Majority charge carrier and minority charge carrier. So majority charge carrier devices, the example is MOSFET and Schottky diode. Whereas minority charge carrier devices, we are having the n number of devices here: diode, SCR, GTO, IGBT. All these are the minority charge carrier devices, right? Sometimes they ask the question, right? Next, number of terminals in the device. So based on the number of terminals in the device, there are 2 types: two terminal devices and three terminal devices. Alright. So two terminal devices were having power diode or a diode. It is a two terminal device. Whereas all other devices are three terminal devices. Check MOSFET, IGBT, GTO, SCR, etc. All these devices are having three terminals. Okay, only diode is having a two terminals. Next, based on the polarity of voltage blocking. So based on polarity of voltage blocking, there are two types, unipolar and bipolar. Unipolar and bipolar. Unipolar means a device is said to be unipolar if it blocks either forward voltage or reverse voltage during its off state. Means when your device or your switch will be in a off state, at that time if your switch is able to block only forward voltage or reverse voltage, then it is known as a unipolar switch. And bipolar switch means when the switch is in a off state and if the switch is able to block forward as well as reverse voltage during off state, then it is known as a bipolar switch. So examples of unipolar switch, yes, diode is a unipolar switch. Your transistor family devices, BJT, MOSFET, IGBT, all these are unipolar devices, right? And bipolar devices, thyristor family devices like SCR, GTO, TRIC, all these are bipolar devices. Okay. Next classification is based on the direction of current conduction. So based on the direction of current conduction, there are two types, unidirectional and bidirectional devices. Yes, unidirectional and bidirectional. Yes. So what is a unidirectional device? A device or a switch is said to be unidirectional if it carries or if it conduct positive current or negative current during its on state. Be careful. For unipolar, bipolar, in the definition I use the word off state. Here on state. Okay. So if switch is in a on state and if switch conduct only positive or negative current, I am saying or, then it is known as a unidirectional. Bidirectional means the switch during on state carries positive as well as negative, right? Positive and negative current during on state is known as a bidirectional switch. So examples of unidirectional switch, diode. Diode is a unidirectional switch. SCR, unidirectional switch. GTO is also unidirectional switch, right? Your transistor family devices, BJT, MOSFET, IGBT. All these are unidirectional devices. And bidirectional, TRIC is a bidirectional device. All right. Yeah. So please go through this. Sometimes they have asked questions based on this information. Okay. Right. Next. Now let us recall the thyristor. Thyristor is a family of devices consisting of 4 layers and 3 junctions. Thyristor is not a single device. Strictly speaking, thyristor consists of number of devices which are having 4 layers and 3 junctions. It is a family of devices. But very first invention of the thyristor family, very first member of the thyristor family is a SCR, right? So that's why your SCR is the most popular silicon controlled rectifier, right? It is having 4 layers and 3 junctions. Right? It is a PN device, right? And 3 terminals. Which are those 3 terminals? Anode, cathode, gate. Anode, cathode and gate. And junctions are J1, J2 and J3. Alright? Yes. So this is simple SCR we are having. Now biasing of the SCR. Biasing means what? Biasing means connection of external supply across the device. So there are 2 types, forward biasing and reverse biasing. So when SCR is in a forward bias mode, which junctions will be in a forward bias mode and which junction will be in a reverse bias mode? Yes, can anyone? When SCR is in a forward bias mode, then out of the 3 junctions, which junctions will be in a forward bias, which junctions will be in a reverse bias? Yes, can anyone? Yes, it is simple. Yes, very good. So J1, J3 will be in a forward bias mode. And J2 reverse bias. Right? J1, J3 forward bias, J2 reverse bias. Okay? Right. And similarly, when SR is in a reverse bias mode, then J1, J3 reverse bias. And J2 forward bias. Right? J2 forward bias. Next, so we can turn on the SCR when SCR is in a forward bias mode. Okay? Next, now VI characteristic of the SCR. Yeah, you might have come across this type of characteristic, right? So it is a plot between voltage across SCR, current flowing through the SCR. This first quadrant characteristic indicates SCR is in a forward bias mode. Third quadrant characteristic indicates SR is in a reverse bias mode. Alright. Now here, this OM, this curve OM, it indicates forward blocking mode of the SCR. This, from this point, let me write it as N, and this is K. NK indicates forward conduction mode. And similarly, this OX, it indicates reverse blocking mode. This is reverse blocking, this is forward blocking, and here it is a forward conduction. This is a forward conduction, right? So some theory questions they have framed. As the gate current of the SCR increases, the forward breakover voltage decreases, right? More the gate current, lesser will be the voltage that is required to turn on the device, right? Next, based on the definition of latching current and holding current, they have framed some questions. Latching current means what? It is a minimum anode current required to maintain SR into on state immediately after SR is turned on using the gate signal and gate signal has been removed. Means at the instant of removal of the gate signal, whatever the minimum value of current that should flow through SCR in order to maintain SR into on state is nothing but latching current, right? We know SR is a semi-controlled device, na? Right? Once my SCR turns on by using gate signal, and if I remove the gate signal, then also my SCR will continue into the on state. But be careful, at the instant of removal of the gate signal, the minimum current that should flow through the SCR is equal to your latching current, right? That current should be greater than or equal to latching current, right? Then and only then your SCR will be maintained into the on state. So latching current is associated to the turn on of a SCR. Holding current, it is the minimum anode current required to maintain SCR into on state, otherwise it will turn off. Means it is like, suppose this is your SCR, this SCR is already in a on state, I have removed the gate current long back. After removal of the gate signal also my SCR is continuing into the on state. And now if my SCR current becomes less than the holding current value, then my SCR will again come back to the off state. So holding current is associated to the turning off of a SCR. Latching current is associated to the turning on of a SCR. IL associated to turn on. IH associated to turn off. Turn off. Generally, IL is greater than IH. IL value is greater than that of the holding current value. Now, related to the latching current value and the minimum gate pulse width required, some questions they have framed. Okay, right. Next, turn on methods of the SCR. We are having 5 turn on methods. Forward voltage triggering. Yes, forward voltage triggering. What we are doing in this method? We are maintaining the forward voltage across SCR, and the forward voltage value should be sufficient or should be equal to VBO. What this VBO indicates? VBO means forward breakover voltage. So here what it indicates, as I go on increasing the forward voltage across SCR, right? We know J1, J3 forward bias, J2 reverse bias. Okay. As I go on increasing the forward voltage across SCR, as junction J2 is in a reverse bias mode, so as the forward voltage increases, the width of the depletion layer across junction J2 increases, and when the forward voltage across SCR becomes equal to VBO, that is a forward breakover voltage, then the breakdown of depletion layer across junction J2 takes place and your device starts conduction. Means without gate current also I can turn on the SCR, but what is the requirement? I need to apply the voltage which is equal to VBO, and generally this voltage value VBO is high. So that's why in practical case this triggering method is not preferred. Means simply what we are doing in forward voltage triggering, we are maintaining a high forward voltage which is equal to VBO, right? And at that particular voltage, the breakdown of the depletion layer across junction J2 occurs and your device starts conduction. But the drawback of this method is the required voltage to turn on the device is high. Means VBO value in device datasheet, the manufacturer of the device gives the value of the VBO, value of the latching current, value of the holding current, etc. Okay. So VBO value is generally high. Therefore, this method is not preferred in a practical case. All right. Second method is gate triggering. Second method is a gate triggering. In this method, we are circulating the gate current in a gate cathode circuit of SCR. In a gate cathode circuit of SCR, we are circulating the gate current, right? And this is the most popular triggering method. This is the most popular triggering method. Third method is dV by dt triggering. Due to the high dU by dt, my SCR is start conduction. Having relation when forward voltage is maintained across SCR, then your junction J2 acts as a capacitor. Okay, so therefore Cj is a junction capacitance. Okay, I don't want to go into that. Okay, so dU by dt triggering, simply we are increasing the dU by dt. How to increase the dU by dt? dV indicates change in voltage, dt indicates change in time. So if I want high dU by dt, means I need to increase the value of voltage by a large amount in a short time span, so that I can get the high value of dV by dt. Okay, right. Fourth method is temperature triggering. Yes. In this method, we are increasing the temperature of the device, and we know SCRs are having the negative temperature coefficient. So therefore, as temperature increases, the resistance of the device decreases. As resistance decreases, device current, or initially it is a leakage current, right? Leakage current increases. Leakage current increases, so device power loss increases. Power loss in device increases. Power loss increases, heat generation increases. And heat generation increases, then again temperature will increase. Means your device will enter into this loop. I am saying as temperature increases, the resistance of the device decreases, because your SCR is having a negative temperature coefficient. So if temperature increases, resistance decreases. Resistance decreases means leakage current flowing through the device increases. More the leakage current, more power loss. More power loss causes more heat generation. More heat generation will further increase the device temperature. So your device will enter into this loop, and your device current increases from leakage value to the finite value, that is a high value. Like this your device will turn on. And fifth one is light triggering. Light triggering is used only in LASCR, light activated silicon controlled rectifier, or it is known as LTT, light triggered thyristor. This is specifically application oriented method. This is used only in case of LASCR. LASCR stands for light activated silicon controlled rectifier, or it is also known as light triggered thyristor. Light triggered thyristor. All right. Yeah. Next, we cannot use this method for a general SCR. Okay. For LASCR, we are having the different construction. We don't have a gate terminal there. Okay. Right. So in that, most popular triggering method is gate triggering. Gate triggering. Next, protection of SCR. So as long as SCR is considered, we are protecting it against over voltage. Yes, how to protect SCR against over voltage? For that, varistor is used, or sometimes they have asked the question, voltage clamping device. Varistor is a one kind of voltage clamping device. Okay, it is used. Next, overcurrent. For overcurrent protection, we are using fast acting current limiting fuse, FACLF, and circuit breakers. FACLF stands for fast acting current limiting fuse, and circuit breakers. These are used. Okay, we know simple principle of operation of a fuse, right? Every fuse is having some current rating. If the current flowing through the fuse becomes greater than the rated current, the material will get melt and it will create an open circuit. Next, third is high dU by dt. High dU by dt protection. How to protect SCR against high dU by dt? RC snubber circuit is used. Right? And high di by dt. Yes, how to protect SR against high di by dt? Yes, can anyone? How to protect SR against high di by dt? Yes, for that, yes, correct. Inductor is used. Inductor is used. Okay, right. So some theory questions they have asked based on this, right? Next, this is a anode cathode protection of SCR. Apart from that, we are protecting gate cathode circuit of SCR also. It is known as a gate protection. Gate protection. Yes. In the gate protection, we are providing over voltage. For over voltage protection, a Zener diode is used. Second is over current protection. For over current protection in a gate cathode circuit, a small resistor is used. Here fuse is not required because in a gate cathode circuit your current range is hardly in milliampere, right? So here high current value, over current value in a gate cathode circuit and over current value in a anode cathode circuit, both are having a very huge difference. So that's why in anode cathode your over current can be in kiloampere. So that's why we require fuse. In this case, over current is having comparatively very small value, right? So therefore, a resistor can do the job. Next, protection against noise signal. Yes, why the protection against noise signal is required? Because due to the surrounding noise, there is a possibility of induced EMF in a gate cathode circuit of SCR. And because of that, your SCR may turn on. So to avoid this, we need to protect it against a noise signal. So how to protect? So for that, RC filter is used. RC filter is used. Right? RC filter is used. Apart from that, in general, we protect SR against the temperature also, na? Right? So for that, we are using heat sink. You might be knowing heat sink. Heat sink is used to limit the temperature of device. To limit temperature of device. Next, commutation of SCR. Commutation means simply turning off a conducting SCR. That is nothing but a commutation. So how to turn off the SCR? First of all, according to the definition of holding current, we know holding current means what? It is a minimum anode current required to maintain SCR into on state, otherwise it will turn off. So if current flow through the SCR becomes less than the holding current, then your SCR will turn off. Now, so how to turn off the SCR? So first thing is, your SCR current should be less than holding current value. And recall the dynamic characteristic of SCR during turn off. So there we are having the conclusion like only reducing the SCR current below the holding current value will not turn off your SCR successfully. So after this, we need to maintain the reverse voltage. We need to maintain reverse voltage across SCR. We need to maintain reverse voltage across SCR for time TC, that should be greater than or equal to TQ. TC means circuit turn off time. TQ means device turn off time. Now we are having the different methods or types of the commutation. Natural commutation, types of commutation. natural commutation, natural commutation means here your SCR turns off due to the nature of source. So that's why it is known as a natural commutation. When the input source or the source is alternating AC, then in that case the SCR turns off due to the nature of source. So tell me the circuitries where input is AC. We are having a AC to DC converter, that is a rectifier. Yes or no? Right? We are having a AC voltage regulator. Right? So in those circuits a natural commutation is used. So I am saying rectifier, AC voltage regulator, and step down cycloconverter. In these circuits, natural commutation is used. Only in step down cycloconverter, no step up. In case of step up cycloconverter, you require a forced commutation. You require a forced commutation. So sometimes they ask the question, right? So be careful. Second is forced commutation. Forced commutation means here your SCR turns off due to the external circuitry, and that external circuit is used to turn off the SCR. So that circuit is known as a commutation circuit. So here SCR turns off due to the commutation circuit. Commutation circuit means external circuit. We need to add the additional circuit elements to turn off the SCR. But whereas in a natural commutation, additional circuit elements are not required. SCR turns off due to the nature of source. Here for turning off of a SCR we require additional circuitry. So forced commutation is used when input to the rectifier is a DC, right? So your DC to DC converters, that is choppers, inverters, DC to AC. The circuitries in which input is DC, in that case we need to go for forced commutation circuit, right? In case of forced commutation, we require additional circuitry to turn off the SCR. In natural commutation, no additional circuitry is required. So therefore, if you check, in a practical case, we are using SCR specifically in rectifiers. We are using SCRs in AC voltage regulators and in step down cycloconverters, right? If I want to use the SCR in choppers or inverters, then in order to turn off the SCR, I require additional circuitry. If I add the circuit, then what happens? The cost of your converter, that is chopper and inverter, will increase. So therefore, generally in choppers and inverters, SCRs are not preferred. Then which devices we are using here? We are using here fully controlled devices. Fully controlled means your transistor family devices like power BJT, power MOSFET, IGBT. These devices are used in choppers and inverters. But whereas in rectifiers we are using SCRs, right? Because in order to turn off SCR, here we need not to go for additional circuitry. Okay. Next, third is load commutation. Load commutation. Load commutation means SCR here turns off due to the nature of load. But for load commutation, we require the load RLC and it should be underdamped. RLC underdamped load is required for the load commutation, right? In inverters, we are having the RLC load, and in that the load commutation is used. So in one of the examination they ask the question, right? For load commutation, which of the following conditions are required? So first thing is load should be RLC and it should be underdamped. It should be underdamped. Okay, right? So these are the types of the commutation. Types of the commutation. Next, Your forced commutation is required in step up cycloconverter also. Step up cycloconverter. In step up cycloconverter, forced commutation is used. Next. Yeah. Next we are having gate characteristic of SCR. Gate characteristic give the safe operating area for gate cathode circuit. Gate characteristic of SCR, it gives the safe operating area for the gate cathode circuit of SCR, right? Generally the manufacturer of the device print this characteristic in a device data sheet, but some simple question they have asked based on the gate characteristic, some numerical questions, okay, right? Here related to the gate characteristic, one expression is there, important expression, PG average, average gate power dissipation is duty cycle D into PG max, and PG max is equal to VG into IG, okay, right. So based on this expression they have asked the question, okay, right. I don't want to go in detail here, what is the characteristic, how to draw the characteristic, only some important points I am writing here. Next, thermal modeling of SCR. So thermal modeling of SCR, this is your SCR. In practical case, how we are mounting the device. This is your device, SCR, or you can say any semiconductor device. Let us consider here it is a SCR. This is a body of SCR, right? We are mounting it, we are placing it on a case. Case is like a supporting structure, right? After that, this structure is we put on the heat sink, okay, and this is your ambient or a surrounding temperature. So we are having four nodes, junction, case, sink and ambient, and related to that we are having these expressions, P average is equal to Tj minus Tc upon theta Jc, etc. Okay, so this expression is important. Based on this expression they have asked us some questions, okay, right. Next, so other switching devices we are having power BJT, power MOSFET, IGBT. These three are transistor family devices. These are transistor family devices. Next, SCR, GTO, TRIAC. These are thyristor family devices. Right, and apart from that we are in power diode. Correct? Yeah. So SCR in detail you are having study. For other devices it is like only introductory part you are having, okay, right. So which device is unipolar, which device is bipolar, unidirectional, bidirectional, semi-controlled, uncontrolled, fully controlled, okay. So please go through these types or the characteristics of the devices. Next, let us discuss some questions. The gate triggering circuit shown below has the specifications IG mean is 100 milliampere and VG mean is 2 volt. Then V trig means this voltage V trig they are saying V trig should be, and for this voltage they have given the 4 options here. So first of all let us understand the question. Here they are asking minimum current required, gate current required to turn on the SCR is 100 milliampere. So this is my SCR, this is a anode of SCR, here it is a cathode of SCR, and this is a gate terminal, this is a gate terminal, right. Now if I want to turn on this SCR, the minimum current required in this branch, that is IZ, this is gate terminal na, so current here is IZ. So what is this current here required? 100 milliampere. 100 milliampere means 0.1 ampere. If current here is less than 100 milliampere, then your SR will not turn on. Alright, this is the one thing. Next, VG mean. VG mean means minimum voltage required between gate and cathode terminals of the SR is 2 volt. Then and only then your SR will turn on. Okay. So here they have given, yes, yeah, this is 0.1 ampere, and between gate and cathode terminal, what is the voltage? 2 volt. This voltage is 2 volt. Right. Now potential difference between these 2 points is 2 volt, and here current is 0.1 ampere they have given. And now they are asking what is the V trig value. V trig value. It is a simple network theory problem, network analysis, right? Electrical circuit analysis problem. That's it. Now here tell me, if this voltage here is 2 volt, right? Then what about the voltage across this 30 ohm resistor? Yes, voltage across this 30 ohm resistor. If this is 2 volt here, this is plus and here it is minus. If this voltage is 2 volt, the voltage across this 30 ohm resistor is also 2 volt, na? Right? So can I say that this voltage is also equal to 2 volt, right? Now can I find the current flowing through the 30 ohm resistor? This is I1, right? So I can write I1 is equal to 2 upon 30, which is equal to 1 by 15 ampere. 1 by 15 ampere. I am saying this is 2 volt, so therefore this is also 2 volt. Now tell me, if here it is plus, here it is minus, if this is 2 volt, this diode will become reverse bias, na? Cathode is at higher, anode is at a lower. So diode will remain in a off state. So if diode is in a off state, what is the current? 0. Now here current I1 is 1 by 15. This current is 0. Here current is 0.1. So can I say that if this current is 0.1, what about the current here? The same current, na? 0.1 ampere. Because current here is 0, so whatever current here, the same current will flow here. Right? Now this is 0.1 ampere, this I1 is 1 by 15. So can I find this current? Let me write it as I2. Yes, I2 is equal to I1 plus 0.1. So I am writing here I2 is equal to I1 plus 0.1. So therefore it is 1 by 15 plus 0.1, right? 1 by 15 plus 0.1. So it is equal to 1 plus 1.5, that is 2.5 upon 15. 2.5 by 15. So it is equal to 1 by 6 ampere. So I2 is 1 by 6 ampere. Now our task is to find this V trig, na? So can I write this V trig is nothing but this voltage which is equal to 2 volt plus voltage across this 30 ohm resistor. And what is the voltage across 30 ohm resistor? I2 into 30. So I can write V trig. So therefore V trig is equal to I2 into 30 plus 2. 2 means this voltage, this voltage is 2 volt, right? So therefore this voltage plus this voltage is nothing but V trig, is nothing but V trig. So I can write it as I2 is 1 by 6 into 30 plus 2. So if you simplify it, you will be getting it as 7 volt, right? 7 volt. So if you check the options, option A is the correct option, right? Yeah. Next, which statement is true for latching current? It is related to turn off process of the device. It is related to conduction process of device. It is related to turn on process of the device. It is related to conduct at full voltage level. Yes. Which statement is true regarding the latching current? Can anyone? Regarding the latching current is associated to the turn on of a device, na? Right? So regarding the latching current, if you check, it is related to turn off. This is not true. It is related to conduction process. No, it is related to turn on of a device, right? Turn on of a device. So option C is the correct option, right? Correct option. Good. Next, the snubber circuit is used in thyristor for triggering du by dt protection, di by dt protection, phase shifting. Yes, we discussed na. Snubber circuit, RC snubber circuit is used to protect SR against du by dt. So option B is the correct option. Option B is the correct option, right? Yeah. Next, if the gate current of an SCR is increased, its forward breakover voltage VBO will, as gate current increases, the forward breakover voltage, yes, it will increase or decrease. As gate current increases, the breakover voltage in the sense the voltage required to turn on the device, it will increase or decrease. Come on. Yes, as more the gate current, lesser will be the required voltage to turn on the device. Okay, so gate current increases, this will decrease. So therefore, if you check the options, option B is the correct option, right? Option B is the correct option. Next, yeah. So these are some questions related to the chapter number 1 and some important points we discussed. Let us have some discussion on AC to DC converter. Okay, right. Here different types of the AC to DC converters: single phase rectifier, three phase rectifier. In single phase, again uncontrolled, controlled, uncontrolled and controlled there are, right? And again we are having in uncontrolled single phase half wave, single phase full wave, etc. Okay, right. Based on the number of pulses in output voltage waveform. So based on the number of pulses in output voltage, we are having the different types of the rectifiers, like single pulse or one pulse rectifiers. Second is two pulse rectifier. One pulse rectifier. Second is two pulse rectifier. Third is three pulse rectifier. Fourth is six pulse rectifier. And fifth is 12 pulse. Right? So as long as your syllabus is considered, you are having only one pulse, two pulse, three pulse and six pulse. Okay, 12 pulse is not there. Now one pulse rectifier, why it is known as a one pulse rectifier? Because in the output of this rectifier, we are getting only one pulse for one input cycle of the supply. Means 0 to 2 pi my supply is completing one cycle na, and corresponding to 0 to 2 pi in the output of this rectifier we are getting only one pulse. So that's what is known as a one pulse rectifier. For these rectifiers, output pulse frequency or ripple frequency is equal to same as that of supply frequency. F0 is equal to Fs. F0 means output ripple frequency, or it is also known as a pulse frequency, which is equal to Fs means supply frequency. So which rectifiers are known as a one pulse rectifier? Your single phase half wave rectifier. Single phase half wave rectifier is known as a one pulse rectifier. You can recall single phase half wave rectifier. It gives only one pulse in output for one input cycle. For one input cycle. So one single phase half wave rectifier. Next, two pulse rectifier. Two pulse rectifier, it gives two pulses in output for one input cycle. Means when input completes one cycle, my output in the rectifier is having two pulses. So here output pulse frequency or ripple frequency is 2 times the supply frequency. 2 times the supply frequency. So which rectifiers are known as the two pulse rectifiers? Single phase full wave rectifier. Single phase full wave rectifier, right, are known as a two pulse rectifiers. They have asked the question in single phase half wave rectifier, in single phase full wave rectifier, what is the relation between F0 and Fs? So be careful. F0 is Fs in half wave, F0 is 2 Fs in full wave. Next, three pulse rectifier. Corresponding to one input cycle, it gives 3 pulses in output, right? So therefore it is known as a 3 pulse. So what is the output frequency? 3 times Fs. Output frequency in the sense output ripple frequency, right? Because my expectation is, this is a rectifier na, AC to DC converter. My expectation is output should be flat DC, right? But in practical case, whether we are getting the flat DC as output, no, my output is a pulsating DC. My output is a pulsating DC. So it is having a pulse frequency, or it is known as a ripple frequency. So which rectifiers are known as three pulse rectifiers? Three phase half wave rectifier. Three phase half wave rectifiers are known as a three pulse rectifiers. Next, 6 pulse rectifiers. F0 is a 6 into Fs. It gives a 6 pulses in output for one input cycle. So three phase full wave rectifiers are known as 6 pulse rectifiers, are the 6 pulse rectifiers, okay, right. And similarly 12 pulse rectifiers, F0 is equal to 12 into Fs, 12 into Fs. In a 12 pulse rectifiers, 2 3 phase rectifiers are connected in cascade, okay, and then we are getting the 12 pulse rectifiers. Next, based on the quadrant of operation. So based on quadrant of operation, there are various types: single quadrant rectifiers, two quadrant rectifiers, and 4 quadrant, okay, right. So single quadrant, output voltage, output current. In these rectifiers, output voltage, output current, both are always positive. V0 and I0 are positive, right. Generally your semi converters gives first quadrant operation. This is the first quadrant, na? Right. So first quadrant operation, semi converters operates in first quadrant, right. Second, two quadrant is rectifiers. Some rectifiers gives output voltage positive as well as negative, but output current is only positive. So this is your two quadrant operation, right? So first and the fourth quadrant, na? Right? So that's why it is a two quadrant rectifiers. So which rectifiers gives this type of operation? Your full converters, single phase full converter, three phase full converter, and three phase half wave rectifier. Operates in first and fourth quadrant. First and fourth quadrant. Sometimes they ask the question, you can refer previous year question papers, you will get the questions based on this. Next, so first quadrant or the one quadrant, two quadrant, right? Next, four quadrant. Four quadrant means in all four, 1, 2, 3 and 4. Right? Four quadrant. So which rectifier gives this kind of operation? we're having a dual converter. Dual converter operates in all four quadrants. Dual converter operate in all four quadrants. Dual converter means simply it is a anti-parallel or back-to-back connection of two full converters. In dual converter, two full converters are connected in anti-parallel or back-to-back. In one of the examination, they asked the question on this statement. In dual converter, two full converters are connected in series, parallel, anti-parallel, etc. Okay, so anti-parallel, or you can say the back-to-back connection. All right. Next, let us recall some circuit operations. In short, let us discuss single phase half wave control rectifier with purely resistive load. So this is my simple circuit. It consists of supply voltage, which is a pure sinusoidal, load is a resistive, and this is your thyristor T, right? Control rectifier, it uses the controlled switch. If I replace thyristor with diode, then it will become uncontrolled rectifier. Very simple circuit, right? So for this circuit, this is my supply voltage waveform, this is the gate signal, output voltage, load current, and thyristor voltage waveform. Okay, right? I don't want to go in these waveforms now, right? So regarding these important points, so on which expression they have asked the questions, okay, let us discuss. So important points are V0 average value of output voltage, important one, okay, V0 average. So if I want to find the average value of output voltage, then how to find? It is 1 by 2 pi, periodicity is 2 pi, integration from alpha to pi, 1 by 2 pi, integration from alpha to pi, Vm into sine of omega t d omega t, right? So after simplification you can get Vm by 2 pi into 1 plus cos alpha, V0 average. So as long as the rectifier chapter is considered, V0 average expressions are important. So most of the questions they are asked on V0 average. Regarding V0 RMS, rarely they have asked the question, okay, but most of the questions are on V0 average only, okay. Next, second is peak inverse voltage, PIV rating, PIV rating of diode. PIV stands for peak inverse voltage, it is equal to Vmax. What is the peak value of this reverse voltage? It is Vmax, right? So regarding circuit turn-off time, you will not get any question, don't worry about this, okay. Circuit turn-off time for Genco, Transco, even your in Polytechnic lecture examinations, they have not asked the questions, okay, but for GATE ESC, they have asked the questions on circuit turn-off time. So if you refer the notes, then you can simply skip the circuit turn-off time, how we have written the circuit turn-off time expression, that you can skip, okay, that is not required. But V0 average, conduction time of thyristor, PIV rating of the thyristor, these are some of the common expressions, okay, right. Next, single phase half wave control rectifier with RL load. If load is RL, then what will the change? You will be having some short negative pulse here, right? Pi to beta. Beta is known as the extension angle, and because of that negative pulse, your average value of output voltage decreases. It decreases, okay, right. So these are some waveforms. Effect of inductive load, average output voltage decreases, just now we discussed. Input power factor reduces, load current I0 waveform gets distorted, and load performance deteriorates, okay. So next, input power factor reduces, it is having the relation with your input power factor for RL and RLE load. So for finding the input power factor, if load is RL and RLE, then we are using the expression distortion factor and displacement power factor. Okay, right. Yeah, anyways, this is RL load with freewheeling diode. Why we connect the freewheeling diode here? Because without freewheeling diode, my output voltage is having some small negative pulse na, and because of that my output voltage, load voltage decreases. So to overcome this, we are using the freewheeling diode. So if you check, if I use freewheeling diode, no negative pulse is present here. Okay, no negative pulse. Yeah, yes, advantages of freewheeling diode: output voltage increases, input power factor improved, load current waveform is improved, and performance of rectifier is better, right? Next, single phase full wave control rectifier. In full wave, again there are two types, midpoint and bridge rectifier. Okay, in full wave there are two types. One is a midpoint rectifier and second one is a bridge rectifier. In practical case, we are using only bridge rectifier, because in midpoint rectifier the PIV rating of switches is 2 times Vmax. Here PIV rating of switches is Vmax. Please listen. In practical case, we are using only bridge rectifiers. We are preferring only bridge rectifiers. In midpoint rectifier, the peak inverse voltage rating of the switches is 2 Vmax. Here peak inverse voltage rating is Vmax. Here in midpoint rectifier, we require the additional transformer. At the secondary side of the transformer, we require a center point tapping, right? So because of the transformer, the weight and size of this rectifier is increases. Here transformer is not compulsion, but here we require specially designed transformer, and the transformer should have secondary side midpoint tapping or center tapping. So therefore weight and size increases. Now tell me, here peak inverse voltage rating is 2 Vmax, here peak inverse voltage rating is Vmax. If I compare the switches here and switches here, which switches will be more costly? Yes, can anyone? If I compare the switches here with PIV rating of 2 Vmax and the switches with a PIV rating of Vmax, which switches will be more costly? Yes. Which switches will be more costly? Yes, yes, correct. Yes, the switches in midpoint rectifier are more costly. Why? Because their voltage rating is high, PIV, right? So more the rating, more will be the cost of the device, right? So therefore here switch cost is more. Additional transformer we are using, specially designed transformer, so its cost is also more. So therefore overall the cost of midpoint rectifier is more. Here cost is more. Comparatively here less costly you can get. And one more part, as here we are using the transformer, and recall from the electrical machines, transformers are having the primary side and the secondary side winding. Both side windings are having some leakage impedance na? And most of the part of the leakage impedance is inductive in nature. So therefore here operating power factor of these rectifiers is poor, but comparatively here we are getting the better operating power factor. So if you compare these two, more weight, more size, more cost, operating power factor is poor. So therefore these rectifiers are not preferred in practical case, whereas we are preferring the bridge rectifiers. Right? Yeah. So this is the circuit diagram for midpoint rectifier with purely resistive load and some waveforms. Okay, right. So again V0 average we can easily find, right. Next, single phase full wave rectifier, bridge type now, R load. Output voltage waveform in case of midpoint and a bridge, you are getting the same, but the thing is here cost is less, right? Yeah. So same waveforms we are getting. Again V0 average, peak inverse voltage rating, etc. Right? Next, RL load. If I use RL load, then I am getting this type of small negative pulse. Okay, right. because of that my output voltage decreases. Now this type of conduction is known as a continuous conduction. Sometimes they give, you don't have in syllabus this type of the I0 waveform. Instead of that you are having highly inductive load type waveform. Sometimes they use the word highly inductive load. Highly inductive load means your load current is a constant, this type of constant. Now my load current is constant and highly inductive load, what is the relation? Please listen. We know the inductor is the element which opposes the sudden change in current. Yes or no? Inductor is the element which opposes the sudden change in current. If my load inductor value is a high, if my load inductor value is high, opposition offered by the inductor to change in current is high. If my load inductor offers a high opposition to change in current, means my load inductor is not allowing the load current to change. So therefore I am getting this type of current waveform. Please check this current waveform. Is there any change in the load current waveform you are observing? No change. So if load is highly inductive, your load current is always constant. But whereas if you check this type of waveform, there is a change in a slowly increasing, decreasing, increasing, decreasing. This is a changing type of the waveform. If my load inductor is high, means I am getting this type of the constant current waveform. More the load inductor, more will be the opposition offered by the inductor to change in current. So no change in the load current, no change in the inductor current or a load current, right? Current flowing through inductor is nothing but your load current, is nothing but load current, right? Now if load current is this type constant or the continuous current, then you are getting this type of output voltage waveform. Okay, in continuous cycle it will be like this. So for this waveform, what is the V0 average? 2 Vm by pi into cos alpha. 2 Vm by pi into cos alpha. Okay, you can derive it, yes, but this expression is important, right? Yeah. Next, RL load with freewheeling diode. If freewheeling diode is present, then no negative pulse. You can check. Output voltage waveform is same as that of the R load. Okay, right. Yeah. These are the advantages of freewheeling diode. Next, single phase semi converter. So bridge rectifier is also known as a single phase full converter, and there semi converter. Difference between semi converter and full converter. In full converter and in semi converter we are having the bridge configuration only, but in full converter all the 4 switches are thyristors or the SCRs. In a semi converter, out of the 4 switches, 2 will be the thyristors, 2 will be the diodes. Okay, so here semi converter there are 2 types, symmetrical and asymmetrical. Okay, so this is a symmetrical type semi converter. Why it is a symmetrical? You can check. This is the first leg of the rectifier, this is the second leg of the rectifier. In each leg we are having 1 thyristor 1 diode, 1 thyristor 1 diode. So therefore it is known as a symmetrical. And why it is a semi converter? Because 1, 2, 3, 4, these 4 switches we are having. Out of the 4 switches, 2 are the controlled switches and remaining 2 are the uncontrolled switches. So out of 4, 2 are the controlled switches. So that's why it is a half controlled or semi controlled or semi converter, right? Or semi converter. Next, so now generally semi converters are used with the RL load, generally used with the RL load. Yes, and again this is a asymmetrical type. You can check 2 thyristors in one leg, 2 diodes in another leg. Okay, so this is a asymmetrical type semi converter, right? Yeah. For both these semi converters, output voltage waveform is same. For semi converters, your output voltage V0 average is equal to Vm by pi into 1 plus cos alpha. From waveform also you can derive. And for full converter it was 2 Vm by pi into cos alpha, right? Next. Yeah. Yes. Next, effect of source inductance. Because of source inductance, what happens? During the overlap angle mu, this is your source inductance. During the overlap angle mu, all the 4 thyristors will be in a conduction mode. This is your overlap angle mu. During this, all 4 thyristors will be in a conduction mode. Okay, and because of that my output voltage is getting reduced, output voltage decreases. Yeah. Yeah, here same thing they have given. Okay, right. I will share this PPT here. Yeah. Next we are having input power factor for RL and RLE load. If the load is RL and RLE, input power factor is calculated from displacement power factor into distortion factor, DPF into DF. So what is DPF, what is DEF we are having. Okay, right. Next, these are the some important expressions regarding the second chapter formula sheet. Please go through these expressions before going for examination, because in rectifiers we are having the n number of circuitries, and for every circuit we are having the n number of parameters. Okay, so it is hardly impossible to memorize all the expressions. So instead of memorizing the expressions, it is better to understand the circuit operation, right? Yeah. So these are the some important expressions. Yeah. Let us have some discussion on some questions related to the second chapter. The following phasor diagram represents fundamental components of voltage and current. They have given fundamental component of voltage and current, means fundamental component of source voltage, fundamental component of source current they have given. So here it is phase A, fundamental component of voltage, fundamental component of phase A current they have given, and they are asking, yes, the mode of operation is. So they have given 4 options, mode of operation. So here in one of the examination they asked the question, right? Here we need to understand, this is the voltage, this is the current. Now tell me, angle between voltage and current is less than 90 or greater than 90? It is a greater than 90 degree, right? Now here, if I want to find the source power, PS means the source power, is equal to what? Vs1 into Is1 into cos of angle between Vs1 and Is1. Let me write it as phi 1. Input side of the rectifier is AC. In AC side, how to find the power? V into I into cos phi. Simple. Okay. So this Vs1 means this voltage, Is1 means this current, and what is the angle between these two? It is alpha. So I am writing it as Vs1 into Is1 into cos of alpha. Now tell me here, this angle alpha is greater than 90 degree. If angle is greater than 90 degree, what about the term cos of the angle? If my angle is greater than 90 degree, cos of that angle is negative, na? Yes or no? Recall the cos of alpha or cos of theta waveform. 0 to 90 degree your cos theta is positive. After 90 degree your cos theta is negative, na? So this angle is greater than 90 degree. So therefore this cos alpha term will become negative. If this term is negative, my supply power or the source power is a negative. Now tell me, if my source power is negative, means my source is absorbing the power or delivering the power? Come on. If source power is negative, PS is negative, then my source delivers the power or absorbs the power? Always keep in mind, if source power positive means the source delivers power. Source power negative means source absorbs power. So here source is absorbing the power. Source is absorbing the power, right? Now they are talking about the rectifier, na? If you check in rectifier, my input side is, this is rectifier, input side is AC, output side is DC, right? Now here my source is absorbing the power. Source, this is source, na? And this side is load. My source is absorbing the power, means my power flow will be from DC side to AC side or AC side to DC side. Come on. If my source is absorbing the power, means my power flow will be from load towards source, na? Right? Means can I say that my power flow is from DC side to the AC side? If my power flow is from DC side to AC side, means indirectly this is acting as a source and this is acting as a load now. Now tell me, if this is acting as a source, this is acting as a load, is it like your inverter? In inverter, source side is DC, load side is AC, right? So here power flow is from DC to AC, means like your rectifier is operating as an inverter. Rectifier is operating as an inverter, right? So please be careful. If they would have given this alpha less than 90 degree na, then your power will be positive. Power positive means power will flow from AC to DC. That is nothing but the rectifier operation. Okay. Now power flow is from DC to AC means it is a inverter operation. It is a inverter operation, right? Yeah. AC to DC power flow, rectifier operation. DC to AC power flow, inverter operation. All right. Next, a three-phase fully controlled rectifier fed from 200 volt, three-phase 50 hertz supply. It is fired at alpha equal to 45 degree. The average output voltage is. Straightforward question. It is directly related based on your expression. For three-phase full converter, that is three-phase 6 pulse, V is your average expression, 3 VML upon pi into cos of alpha. So it is equal to 3 into VML means peak value of line voltage. By default, given voltage in a three-phase circuit is line voltage na, RMS value of line voltage. It is a 200. This is RMS value of line voltage. From this, I want the peak value na, RMS to peak. How to find? Multiply that RMS with root 2 upon pi into cos of alpha. Alpha is 45 degree. Cos 45 is 1 by root 2. Root 2 will get cancelled out. So I can write it is equal to 600 upon pi. 600 upon pi, right? Simple question. So option D is the correct option, right? Yeah, okay. So I think we are running out of time. I will share my number here. If you want the notes, you can WhatsApp me. Right? If you want the notes, if you want this PPT, you can send me a message. I will share the GATE ESE notes as well. Even your Janko Transco notes also, if you want, I will share those notes also. Okay? Right. Okay. Thank you. Thanks to all of you.